I want to show you some examples of how do you compute a derivative straight from the definition. So one of the examples that we looked at before was you can take this function y equals f of x equals to x squared. So how do we actually find some derivatives? So let's look at the following question. So can I find the derivative of x squared at the point x equals to 1? And when you're working with computing something from the definition, there's really only one thing that you can do. You have to start by writing down what the definition is. There's really no other way you can get around it. So I have to go straight to writing down the limit. And I can use either definition that I want. And I'll show you how to do this with both. But let's start with limit as x goes to a, and a is equal to 1. Limit as x goes to 1 of f of x minus f of a with a equals to 1 all over x minus a with a equals to 1. And you want to just plug into your function. F of x equals x squared minus 1 squared all over x minus 1. So you need to figure out this limit. So here's where our practice from calculating limits earlier on becomes useful to us. So notice that we can't simply just plug in x equals 1. That won't work. We'd end up with 0 over 0. That's something called an indeterminate form. That means we can't determine the form of the limit just from plugging that in. So what you do instead is, in this case, you have to remember what this graph really is. If you plugged it in, it's going to look like a line with a hole in it. And when you're calculating the limit, you're sort of finding the y value that you would use to plug in the hole. From an algebra perspective, the way you can get around this is you can just factor this expression, x squared minus 1. And so let's try it. So if you remember factoring, x squared minus 1 turns into x minus 1 times x plus 1. A minus b times a plus b equals a squared minus b squared. And then you're going to just eliminate the common factor. When you're calculating the limit, you don't actually have to plug in the value x equals to 1. You're really considering values of x that are close to 1 but not equal to. So it's appropriate to cancel out that factor. So you end up with just the limit as x goes to 1 of x plus 1. And here now you really can plug in, because there's no indeterminate form. You just plug in the number x equals to 1. And you get 2 as the answer. So the derivative of x squared at x equals to 1 is equal to 2. That's telling you the slope of the tangent line of x squared is equal to 2 when you're at the point x equals to 1. So actually what I want to do now is show you that the two definitions of derivative really are the same. So I'll calculate this again using the other definition, using limit as h goes to 0 of f of a plus h, that's 1 plus h, minus f of a, that's f of 1, all over h. And here I plug this in, and I have to plug in 1 plus h in for x. And so I'm going to get 1 plus h squared. The function is whatever your input is, square it. And my input is 1 plus h. I'm subtracting 1 squared, all divided by h. And then I'm taking the limit of that as h goes to 0. So that's this other definition of limit. And whereas the other definition of limit required us to factor, this one requires us to do a different kind of algebra. It requires us to expand out. So if you like factoring, use the other definition. If you like expanding things out, use this definition. And if I expand this out, I'm going to get 1 squared plus 2 times 1 times h plus h squared minus 1 divided by h. And you can see something nice happens. I get 1 minus 1, so those cancel. And finally, I get the limit as h goes to 0 of 2h plus h squared over h. And here you can cancel out an h from numerator and denominator. If you just tried to calculate this limit by plugging in h, you'd run into the indeterminate form. That's no good. So what you do instead is factor out an h from that expression. And that's why we wanted these 1s to cancel. So I factor out the h. So I get h times 2 plus h divided by h. You can cancel those out. You get the limit. H goes to 0 of 2 plus h. And substituting in now h equals to 0, you still get 2. So that's nice that they gave us the same answer. And what I'm going to do now, let's try to make this argument even more general. So instead of just calculating the derivative at x equals to 1, let's just try to, in general, say, okay, what's the derivative of x squared at the point x equals to a, where a could be equal to 1, 2, negative 1, pi, whatever. But I'm just going to notate it by using the constant a, and then that'll give me a formula for the derivative no matter what a is equal to. And you could do it with either definition. I'll go back to limit as x goes to a, f of x minus f of a all over x minus a. So I just did this before with a equals to 1. Now I'm doing it for any number. We call it like a fixed but arbitrary number a. So I take this limit. I plug in x to get x squared. I subtract a squared all over x minus a. And you can see now I need to do this factoring. So I'm going to get limit as x goes to a, and x squared minus a squared, that's x minus a times x plus a, all divided by x minus a. And like before, we get a cancellation, this factor of x minus a. And like before, I get limit as x goes to a of x plus a. And here now I can just plug in the value x equals to a, because there's no division by 0 issue. And I'm just going to get a plus a equals 2 times a. So whatever your x value is, so that you're taking the derivative, the slope of the tangent line is going to be twice that. So x squared gives you, the derivative is twice the x value. So a way that you can write that is if you just skip all the middle work, f prime of a equals 2 times a. So this is, if you like, it's a function whose input is a and whose output is the derivative 2 times a. And when we write functions, it's actually common not to just use a or b. It's more common to use x or y. So you could also, if you wanted to, you could write it as f prime of x equals 2x. You can think of the derivative as a function if you like. So what this argument has shown us is that given y equals x squared, its derivative function is equal to 2x.